So welcome back. Previous lecture we discussed implementation, very simple code that is related to Python. How do we implement a single layer perceptron by using a step function, and then multi-layer perceptron using both PyTorch and TensorFlow. So there we consider the simple like two input features are supplied to the input layer, where the input layer have four neurons, and then the output layer it has only one neuron. We use the input layer, that is ReLU activation function, and the output layer sigmoid activation function. So now let us take the same model we are going to use, and I'm going to explain with a numerical example how the computation happens, right? So here let us take the two inputs like x1 and x2, because the defined model takes the two inputs. So input layer has the four neurons, like neuron 1. These are the four neurons. So then we need the four weights from the each input. That means each input will not be given the equal weightage. So we have to give the different weights. That is based on the importance. So here x1, these are the weights, like inputs passed to this input layer neurons, and similarly x1 x2, right? So now the w1, the weight vector, if you look at this weight matrix of this, so this is like a w11, like these are the weights assigned to the input x1, and whereas these are the weights assigned to the next input x2. So next, and then we have to do the computation, but before we have to add the term bias also. So bias, that is b1, so that the vector b1 is like b11, b12, 13, 14. So next, what need to be done? So we have to, like as we discussed, like a pre-computation and pre-activation and activation. So this, the G1, so G1, that will be the output that is produced, that is like the computation, that is before we weighted sum, like x and x is the input and w1 is the weight matrix, and then we'll add the term bias. So then we'll supply this value to the nonlinear activation function. So next one is, so these four neurons in the input layer produce the values, like if any neuron, that is based on the neuron, whether the neurons get fired or not. If all the neurons, let us say if all the neurons fired, then all these four neurons will produce the four values. So then again we have to assign the weights to all these outputs produced by this input layer neurons. So that gives the weight matrix W2. So W2 has like W31, 32, 34, 33, like this. So then we also need to add the term bias. So that is just only single neuron in the output layer. This is a output layer. So it has only single neuron. So that will take only one bias. So then next we have to calculate this Z2, that is the pre-activation. So pre-activation, that is A1, that is the output produced by this, and then we have to multiply, that is weighted sum of this, and then the term V2. So then we'll get a Z2. So then we have to pass this value to the activation function. So then the value which is produced called as a activation. So now let us take very simple example here. This is a numerical example. So let us take two inputs where x is 0.5 and 0.2, and w1, that is a weight matrix 1. This is w1. Values are initialized like this, random values, and then the bias also, the b1 also need to be initialized, so that the b1 is like this. So then what need to be done? Here we have to calculate this G1. So G1 is a weighted sum and plus adding the term bias. So then, and if you do the calculation, then the G1 that is equal to, this is the way we can evaluate. So these two, like dot product of these two, and then add the term bias, that is this one. Like suppose here you can see the dot product of this one, like this and this part. So 0.5 times 0.1 plus 0.2 times minus 0.4 plus the corresponding bias term is 0.1, and similarly for the remaining all. So then, and these are the values produced. So if you pass these values to the non-activation function, that is a ReLU, then the ReLU produces these values, because as per the ReLU activation function, like suppose ReLU of x, it would produce it produces x if x is greater than 0. It produces 0 if x is less than or equal to 0. Okay, so, and these are the values which are greater than 0, and the remaining two are the negative values, minus, which are less than or equal to less than 0. So that's why for those it has produced the output 0, and for the remaining values it produced as it is x. So this is the way the rectified linear activation function works. So then what need to be done? So we have to pass this. So then, okay, so up to this part is over, right? Up to this part is over. Then we have to consider, right? We have to transform the data to this output layer. So now this is the output that is produced by the ReLU, and then we have to take this W2. This is a W2 weights assigned to all these four. Like these are the weights assigned to these four values, and also we need to take the bias B2. So that is initialized to minus 0.1, let us say. So then we have to calculate Z2, that is weighted sum plus term bias. So that, and if you do the calculation, then the final value, that is Z, if you simplify all these equations, then we'll get the final value, that is minus 0.011. So here the output layer activation function we used is the sigmoid activation function. So then we'll supply this, that is to the sigmoid activation function, that is then it produced the value which is approximately equal to 0.497. So that is the way the data is transmitted, like how the information, like from the input features are multiplied, that is weighted sum of the input features, and how the term bias would be added, and then how what will be the pre-activation, and how and what will be the activation, and what activation functions are playing the role, so that you can take this simple example and you can play with that, so that you will understand more deeper, so that it will be very easy to understand any other complex deep learning models. So thank you for watching this video.